Yes, ma'am.
Okay. Please ask your friends to join the class. So we saw virtual work method for truss, okay? And next we'll see a virtual work method for beam, and we'll do two numericals also, okay? So go through the last class work energy method and this virtual work method. As the name says, virtual work method, you'll apply a virtual load of 1 kilonewton to the point where you need to find out the deflection or displacement. Okay, sorry. 22. Okay, I'll share the content. Okay, I'll share the class. Please type in the chat box. Okay, don't mute yourself, otherwise it create echo. So I'll play the video. Let me know if it is the video and audio is okay or not. Okay, in the by typing in the chat box.
The basis of the virtual work method and its use for calculating joint displacement in trusses were discussed in lecture
Is it okay?
SA21. In this lecture, I'm going to show you how this method can be used to calculate deflection
Audio
and
and video
slope
is
in
fine.
beams.
It is not lagging behind.
Let's start by reviewing the method using
Okay,
a
okay.
truss
So
structure.
I'm starting with this from the start. Okay.
The basis of the virtual work method and its use for calculating joint displacement in trusses were discussed in lecture SA21. In this lecture, I'm going to show you how this method can be used to calculate deflection and slope in beams. Let's start by reviewing the method using a truss structure. Consider this truss. Under the applied load, it is going to displace like this.
So it is just reviewing the
To determine
earlier
the joint
classes.
displacement, say horizontal displacement at C, we place a virtual load at the joint. In this case, a horizontal load at C. Note that the direction of the load corresponds to the direction of the target displacement. If we are seeking to find a horizontal displacement, the virtual load should be horizontal. If we wish to calculate a vertical displacement, the virtual load must be vertical. In this case, external virtual work equals P star times delta, and the internal virtual work equals
So my external work will be P delta into P star into delta. P star is my virtual load, and the deflection of that at that point, that will be my external virtual work. Okay, and my internal virtual work will be the forces in those member due to this load. Okay, forces in the member due to this load into real deflection of these members.
here, F star I is the force in member I due to the virtual load, and delta I is elongation of the member due to the real load. According to the method of virtual work, external virtual work equals to internal virtual work.
Earlier it was 5 members. Now you have
star is the
now you have 7 members. If you see the figure, you have 7 members. That's why they have placed I equals to 1 to the power 7. That means F1 delta 1, F2 delta 2, like F3 delta 3, like that till 7. So that is summation of all the forces into displacement will be your internal virtual work, and the load and the deflection that due to that load will be your external virtual work. Okay.
Virtual load, and F star I is virtual member force due to P star. This is displacement due to the real load, and this is member elongation due to the real load. Now let's turn our attention to beams. Say we have this simple beam.
So let's start with the virtual work method for beams. Okay.
Here is how the beam is going to deflect under the load. Suppose we want to determine the vertical displacement at mid-span. To do so, we should place a virtual load at the midpoint of the beam where deflection is denoted by delta. Then the expression for external virtual work can be written.
The screen is not visible. is it for all of you? The screen is not visible for all of you. Ivan says that screen is not visible. What about others? Please respond. What about others? Screen is visible? Okay, so Ivan, please check your network connection. Okay, please check your network connection, maybe reduced.
As P star times delta. To determine the expression for internal virtual work, we need to know two things: the internal member force due to the virtual load, P star, and the internal member deformation due to the real load, P. What is the main internal force in beams? Bending moment. When dealing with beams, we generally consider bending moment to be the only internal force that contributes to the structure's deflection. But since bending moment is not constant throughout the beam, we need to express it using an equation. Here, the virtual load is placed at the midpoint of the beam. Therefore, the beam's virtual internal bending moment can be written as. Now we need to determine the internal deformation in the beam. To do so, let's examine a tiny segment of the deformed beam. Since the beam has been deformed under the real load, the segment also has a deformed shape. We can treat it as an arc length of a circle. The angle facing the arc length, this angle, represents the internal deformation of the segment due to bending. So, internal virtual work in the segment can be written as m star times d theta. To determine internal virtual work for the entire beam, we need to integrate the expression over the entire length of the beam, like this. But before we can use this equation to calculate internal virtual work, we need to express d theta in terms of dx, since m star is a function of x. Let's start by referring to the length of this segment as dx. This is the infinitesimal length of the tiny beam segment.
So see, a beam is given. Okay, a beam is given. They've applied a virtual load. Actually, this that is the beam with P load. It is at a distance of 6 meter and 2 meter. So we are taking a beam, we'll applying a load at the center, a virtual load P star. Okay, and we have found out the moment equations for two. There will be two. If you go back to the shear force and bending moment diagram, how many sections will be there? There will be one section like this, and there will be one more section at this, right? So for this section, if you consider it from 0 to 4, what will be the moment equation? This one. If okay, they are taking the section from this part. Okay, so you can take from here or you can take from here. Okay, so from for this to this will be the 0, this will be the 4, and this will be the 8. So for this will be the section from 0 to 4, that is this moment equation. From 4 to 8, this will be the moment equation. Okay, so we have found out the moment equation. Now what will be the internal virtual work for the segment? So I am taking a segment of the beam, deflected beam. This is the segment. So for this segment, I am getting the deflection m dash into d theta. Now if I need to find out the deflection of the entire beam, what I'll do? I'll integrate that value. First, I have found out the deflection of a internal virtual work of a small segment, and when I integrate the whole segment, I'll get the internal virtual work for the entire beam. Okay.
Also, let's refer to the radius of the circle containing the arc length as rho. And keep in mind that this deformation is caused by the bending moment produced by the real load. I'm going to show the bending moment as big M. Using simple geometry, we can write d theta times rho equals dx, or d theta equals 1 over rho dx. Now we need to express rho using more familiar terms. There is an interesting relationship between rho and m. When m increases, rho decreases. When m decreases, rho increases. Interestingly, the product of rho and m is constant. More specifically, rho times m equals E times I, where E is the
So if you
material's
go back
modulus.
again to the pure bending case, they have applied that equation del m equals to EI. Okay, pure bending
Elasticity,
equations they have
and
used.
I is the moment of inertia about the axis of bending. Of course, here we are assuming linear elastic material. Then we can write d theta equals m over EI
So your slope will
dx.
be m by EI dx.
Finally, we
Recall
can
from the
write the
earlier
expression
class,
for
we
internal
got the
virtual work for the entire
equation
beam
m by
as.
EI equal to
It
dx.
is important to keep in
So
mind
your
that
internal
m
work will
star
be
is bending
m
moment
star.
equation due to the
The internal work will be m star into d theta. M star will be the moment equations. Generally, you can derive from the shear force bending moment diagram classes. You can get the moment equations for different types of beams, right? For different sections, different parts, you will get the moment equations into d theta. D theta from bending equation we have m by EI equals to dx. So we can place m by EI dx there. Okay, now this integration will have these boundaries 0 to 4, 0 to 4 plus 4 to 8 like this. Okay, you will understand when you will solve the numerical, but so that will be your internal virtual work. External will be P star into delta. Your internal will be moment equation of that beam into d theta, which is m by EI dx.
virtual load, and m is bending moment equation due to the real load. The virtual work principle can now be written as, if we assume a unit virtual load, we can determine delta using equation delta equals the integral of m star m over EI with respect to x, where both m star and m are in terms of x. Let's calculate delta at the beam's midspan. We determined m star for this beam earlier. Here it is. Note that m star and m equations are defined over different intervals.
So this is the moment equation due to virtual load. This is the moment equation due to the real load.
To make the integration work, we need to divide it into 3 parts, as shown below. If we assume a constant EI for the entire beam, we get so vertical displacement at the beam's midspan is. Let's go ahead and calculate vertical displacement under load P as well. Here is the moment equation due to P. It is the same equation we used previously. Now replace P with a virtual unit load. Write the moment equation due to this unit load. This is going to be the same as M equation, where P is replaced with 1. Therefore, the virtual work equation becomes. Here, since the moment equation intervals match, we can write or this gives us delta equals.
So what they asked to find out the vertical displacement under the load. So this is the load P given. Okay, this is the load P given. They have asked to find out the vertical displacement under the load. So this is my load. So I replace this load. This is my bending moment equations for the given load. Okay, and I have replaced this P with 1 star. That means I have replaced this with a virtual load. So these are my bending moment equations. So I got m star. So I can place with m star into d theta. D theta is m by EI dx. So as 1 by EI is constant, I have taken out. I have placed the boundary condition, which is if I take 0 to 6, this is 2, okay, and 6 to 8. Alright, if I take 0 to 6, if I start from here 0 to 6 and then 6 to 8. Okay, so I place the boundary condition, place the moment equations. These x by 4 is my moment equations. X by 4, px 4, and this 6 minus 3x by 4 into that. So I have to use both moment equations for the real load also and for virtual load also. So for that will be the multiplication of and real load and virtual load. So see x by 4 into px by 4. Okay, then here 6 minus 3x by 4 into the load moment equation due to the real load. So moment equation due to the virtual load multiplied by the moment equation due to the real load, and place the boundary conditions for the beam, and I have found out the deflection 6 PEI.
Here is another example. A cantilever beam
Now let's see
subjected to
for the
uniformly
cantilever beam
distributed load.
with UDL.
Let's calculate its
Okay,
vertical
a
deflection
cantilever
at
beam is given to you, and it has assume a constant EI. That means throughout the section, the cross section will be same, and your EI will be same throughout the section. You may get a section in future that like this. The beam is okay. Let me draw once more. In future, you may get a beam like this. This is not exactly correct. Let me. This is uniform cross section, okay, and you may get a beam with different cross section also. So for this portion, your EI will be different. For this portion of the beam, the same beam, but the cross section is different throughout the section. That means the first part of the beam is much thicker than the earlier part of the beam. So what will happen? The EI value will be different for this part, and EI value will be different for this part. Okay, but here it is says that EI is same for the whole section. Okay.
at A. Assume constant EI. We start by writing the moment equation for the beam. Now, remove the real load and place a unit virtual load at A. Write the moment equation due to this unit load. The virtual work method equation is so vertical displacement on the cantilever at A is Suppose we are also asked to determine the slope of the elastic curve at A. This can be done easily using the method of virtual work. Here, since we are looking for slope, denoted by theta, we are going to place a virtual unit moment at A. This way, the product of the rotation and virtual moment is virtual work. So the expression for external virtual work becomes 1 times theta. The expression for internal virtual work remains to be. However, now m star is the moment equation due to a unit virtual concentrated moment applied at A. So the cantilever's rotation at A is We will examine the use of the method of virtual work for calculating deflection in frames in the next lecture.
As we have found out the slope and deflection in earlier classes, we can find slope and deflection from virtual method also. So in the next means I'll continue the class. So I will see this calculate the horizontal displacement and the slope for this beam. See, this is the beam. Actually, this beam is like this, a cantilever beam with different cross section. One is this cross section, and another is this cross section. So it is fixed at this part. So this is the if you place in horizontal plane, so it will be like this. So we'll see the horizontal displacement and the slope at C for this kind of beam, and this for this beam also. Okay. Uh, Let me share again. As I have some network connection, please write your roll numbers in the chat box, okay? I may miss some class, means it might get disconnected, so better all of you are asked to write your roll number in the chat box, please. Anyone left to write the roll number? Okay, we'll see the two problems, okay, for the beam by virtual work method. Okay, there is some network issue in my area, so I'll start a new meeting. Okay, I'll start a new meeting. All of you, please join that meeting. It will be the continuation of the class. Okay.